So thank you very much. So thank the organizers for inviting me to this excellent program. This talk will be based on these 3 papers, with the main author being Kostya Tikhonov, and one of these also Skvortsov was collaborating, and I will briefly touch some other subjects and papers are listed here, and other people who contributed. Since there have been lectures and talks on many-body localization, I decided to skip entirely the introduction. I presume you all know what is localization, what is many-body localization. So that's the only kind of motivation slide. This activity on many-body localization, which so I listed just a few papers. So this is starting from 2005, this activity on many-body localization, especially extended systems with short-range interaction, but there are also related activity actually even earlier on localization, many-body localization in quantum dots in a somewhat different sense, in the sense many-body localization in the Fock space. And then there are systems with long-range interaction, which in a sense interpolate between these 2 limits. And so all these activities revive the interest to localization on tree-like graphs. I will explain what those graphs are. And the questions that one wants to understand are the properties of the transition, properties of both phases, localized and delocalized, the critical regime. And in particular, one of the questions that have been asked is whether the delocalized phase is actually ergodic. So with these motivations, I will consider this model of Anderson localization of random regular graphs. And I will just in a moment explain what is kind of a connection to many-body localization, which is somewhat vague, but still we will see there is a lot of common that these models. So now first definition, yeah, it's very simple. It's a random regular graph is a random graph with constant connectivity. Just define it in this line, yeah, that's it. Connectivity is just a number of vertices that is connected to every vertex. So for example, here it's 3. So locally, if you take such graph randomly, one can prove mathematically that it will be locally a tree-like system, which will look like Bethe lattice or Kelly tree. However, it doesn't have any boundary. Therefore, it should have some loops on a large scale. So typical size of loop scales like log n, where n is the system size. And on such a graph, we consider just a tight binding model, kind of single particle problem, which hops on this very complicated lattice. Yeah, so there is just one parameter of the disorder, the strength of disorder here. So this hopping is unity. And I will consider this model. Now, what is the connection to many-body localization problem? So first of all, the Hilbert space here grows as m. So m is the conductivity, is 3 to the power L, where L is linear size. So it grows exponentially with the linear size. So linear size is the maximal distance between the points here. So like in a many-body system. So you can think about this size here as kind of corresponding to many-body basis states and links between them like interaction matrix elements. And so this is a vague connection. It's not this exact statement. However, there is a much in common, and in some cases we can make it somewhat more rigorous, although still not fully rigorous. But let's in a moment just leave with this motivation. Yeah. So actually, closely related problem of what we call sparse random matrices was considered by Jan Fodor and myself almost 30 years ago, and by using supersymmetry. And what we have shown, and I will sketch the proof adapted to this model that we can see now, is that in the whole delocalized phase, we have the ergodicity, namely the Wigner-Dyson level statistics, and the wave function statistics, they're ergodic in the sense that the inverse participation ratio, if you define it, scales linearly with 1 over n, where n is the size of your Hilbert space. You can think about logarithm of this as an entropy, and it just means that the entropy is just is the logarithm with a maximal possible coefficient. Yeah, the prefactor here scales as the logarithm of this prefactor scales as a square root, 1 over square root of the distance to the critical point. And the meaning of this is, as I will discuss below, with some correlation volume. So when we approach to the critical point, there is a divergent correlation. Okay. So now, before I go to the models, so let me explain difference between different models. There is a lot of sort of confusion in the literature just because people do not understand that these are different questions. So that's so what we will consider is this RG model. It's a finite system, N is large but finite, and we can then study properties of the individual eigenstates like inverse participation ratio. You can consider just a Bethe lattice and simply cut it. Just finite size of Bethe lattice. Yeah, you can ask the same questions. For example, you still can study inverse participation ratio. It will turn out that it's totally different. It's a crazy model. Most of sites are on the boundary, and because of this, you get totally different answers. You will always get some fractalities and all this. So we also know all results. It's related to interesting mathematical problems like front propagation, Fisher KPP equation to those who know, but it's not discussed here, and it's different. Yeah. One can also consider an infinite Bethe lattice model, and actually this one was studied earlier. That's starting from this famous paper by Abhishek, Anderson, and others. So in this problem, you cannot ask a question, what is the inverse participation ratio of given eigenstate? It simply doesn't exist, yeah, because it's an infinite system. You can ask different questions like, what are green functions at finite frequency, or real or imaginary, and we will establish some connection between the problem number 1 and problem number 3. Okay, so there was some motivation for us to do this, which came from numerics that I show here. It was some years ago. So Giulio Beroli and others looked at scaling of the inverse participation ratio with the system size in this model. So that's what they obtained. This, what is shown here, is a fractal exponent that corresponds to the scaling as a function of disorder. So the critical point, as we'll show, is 18 points. So it's here. So it's all delocalized phase. And the exponent 1 would correspond to ergodicity. 0 would correspond just to totally localized state, and everything which is between. So as you see, you find the exponent that changes continuously as a function of disorder in almost the same okay, it doesn't go to 0, but it's in most of the delocalized phase. And here it's even worse. He says that it scales as some log. So basically here he says it's just this exponent is simply 0. So basically this would mean that most of the non-delocalized phase is non-ergodic. Okay, and so there was another paper by these authors, Lukal, Schuler, Kravtsov, Dikio, basically repeated this in some, it's this numerics in slightly different ways. They plot some multifractality spectrum in terms of this f of alpha function, for those who know, singularity spectrum, and state, there are some fixed points here that do not change with the system size, and therefore f of alpha should be non-trivial, this multifractality spectrum in the limit of infinite system size. So we have, and that's the conclusion. It's just a citation of the paper. We conclude that non-ergodicity and multifractality persist in the entire region of delocalized state. Yeah, so that would be very interesting and very intriguing, because it would mean that the non-ergodic, that delocalized phase is always non-ergodic. However, it's totally wrong, and that's what I will try to explain. And I think this slide should teach a lot. One should be very, very careful with numerics on small size systems. Yeah. You can get, well, basically whatever you want to get. And that's if you are not careful enough. Just be careful with this sort of problems by making this sort of conclusions out of numerics on small systems, out of exact diagonalization. Okay, so how do we approach the problem? So first of all, I will show you direct numerics and exact diagonalization, but trying to be as careful as one can. And however, we also can complement by supplemented by field theory approach. And in the limit of large n, I will show that one can derive some self-consistent saddle point equation, which looks like some self-consistency equation, which is fully controlled in the limit of large system size. And this can be studied either analytically, this equation, or numerically by population dynamics method. But this numerics, as I will show, is much, much more efficient than this one. So for this model, we have this luxury of having a different type of numerics, which is much more efficient. But as a result, we can also prove and check what actually exactly, how good is exact diagonalization. Okay, So now let me show first some numerics, our numerics. So what is shown here is the level statistics. That's the same parameter, mean adjacent gap ratio R, that I think you have already seen here, I guess, as a function of disorder for different system sizes going up to sizes here. And your first impression, there is a crossing point here, so there is a transition at 15. This is wrong. As I told you, the transition is somewhere here. And if you look more, so how do you realize this? You should look more carefully here, and then you see that this crossing point actually drifts. With increasing system size, it moves. And you can show it also here. You replot the same data as a function of n for fixed, each curve is for fixed w. And now you see that this curve, okay, so what you see here, this is a weak disorder. It's just Wigner-Dyson, very nice, yeah. It's a stronger disorder. It first looks something intermediate, but then goes to Wigner-Dyson. This one also. But now let's look here. Eh? This also goes towards Wigner-Dyson, but you cannot go to larger system. You simply cannot diagonalize them. But it's clear that this goes that this will continue. But now these curves have minimum here. They go first down and then up. And also this one will also, this is also delocalized. Actually, this goes down towards Poisson, but I claim it's delocalized. It will go up. But one should have a system of enormously large to see it in exact diagonalization. So why do we have this minimum? There is a very good reason for this. It's just kind of RG scaling. Yes? It's for when the system is small, it's critical, and it flows towards the critical point. So it's a critical point, the statistics is Poisson. So it flows down. But then, once it reaches the correlation volume, it realizes that it's on the delocalized side, and the flow changes. It starts to flow to another fixed point, namely the ergodic one. So that's what we see here. Now we repeat this, not repeat, yeah, we do the eigenfunction statistics, what people did in those papers that I showed you. So that's now the plot of inverse participation ratio as a function of the system size. And as you see, so this is we plotted in such a way that if it's constant, so we multiply by n. So when it's constant, it's a good medal. So you see for weak disorder, it's perfect medal. When it's insulator, it should scale here as n with a slope 1. So 25 is definitely insulator, it's scale 1. But let's see intermediate curves, yeah? So this is really, it's not too strong disorder. So you see it first flows up, but then saturates. So this one also first flows up, but then saturates, and so forth. But again, for these curves, we cannot get to such large systems, but they show the same tendency. However, if you take this line, for example, some of this, of course you can feed it by some intermediate slope, and you will get some fractality, but it's just wrong. There is no fractality. It's just because your system is small. So to see it still better, we show flow and fractal exponents with a logarithmic derivative. And then you see very similar picture to what was the level statistics, yeah? So that's weak disorder, somewhat stronger disorder, somewhat stronger, somewhat stronger. So up to disorder like 11, we can reach essentially 1, which is ergodicity. For stronger disorder, there is a tendency in the same direction, but system size is just not big enough, yeah? So if you cut it at your maximal system size, then of course you get some fractal exponent, but it's just fake. Yeah, it's just your system is, you are in the critical regime. Yeah? You don't study the big system treatment. And again, there is a minimum that is magnified here for the same reason as I discussed about. Okay, so now one can try to get a correlation length scaling out here. So basically, this position of the minimum is the correlation volume. Once you reach the correlation volume, the system realizes that it's in a delocalized phase. So one can try to get an exponent. However, it's a very bad way to get an exponent. Its accuracy is very, very bad. So first, you cannot just really get a critical point out of this with a good accuracy. So basically, it's consistent with 1/2 the correlation length exponent that we know analytically, as I will explain. But it's, if you just, it may be 1/2 plus minus 1/2 out of this. That's, but I will show you how to get it with much, much better accuracy from the different method, but you will see how big systems you need to really obtain it with a reasonable accuracy. So we know exact analytical result, and I will show you the numerics. Okay, so now, yeah, there will be a couple of slides with many formulas. So I don't think I want to explain all of them because I will then spend all my time. So let me just give you the idea of this. Yeah? basically, yeah, so I use supersymmetries. Those who prefer replicas can derive from principle the same as replicas, but I prefer doing this. But it's essentially the same. So you can write your observables here exactly. It's a non-interaction system on this complex lattice. You can write everything in terms of some functional integrals with the action, with some quadratic action, in terms of some supervectors phi. That's more or less standard approach to this type of disordered electrons and random potential. Then after this, you can average over your randomness, over randomness of your potential. You can also introduce random hoppings if you want. And after you average, you get some nonlinear action, yeah? Just because the epsilon here is random. If it's Gaussian, you have quadratic term. Once you average over epsilon, you will get quartic term, and something like this. But here, so what you get in the end, it's because you should also average over the connectivity of your system. It's a random graph. So once you do this, you obtain, okay, let me show you what comes in the end. Yeah, you can decouple it by some functional generalization of Hubbard-Stratonovich transformation, what is also typical here. And as a result, you get your average of whatever you want to calculate as functional integrals over some functions, which are functions of a supervector. So this, up to this formula, it's still exact. Yeah, that's there is some nonlinear action that we have, and you integrate over functions supervector, and there is a pre-exponential that depends on the observable you calculate. Yeah? And the crucial thing that you have n here, which is similar to n how you get in mean fields. The difference with mean field, it's much more complicated, so you integrate not over just some magnetization, but over functions. Yeah? So but n, big N here allows you to do saddle point. So yeah, as an example, you calculate, for example, the inverse participation ratio. Inverse participation ratio is extracted as a product of retarded advanced Green's function multiplied by some level broadening eta that you should send to 0. That's it should be sent really to 0 before everything else is done. And as a result, you obtain this formula for the inverse participation ratio, where the prefactor here is some beast. But the crucial thing is that for this g, function g, you can get a saddle point equation, and the saddle point equation is a nonlinear integral equation. So as you see, this g is related to this functional f, which which was on the previous slide, which contains the function g to some power. G to the power m+1, and m+1 is related to connectivity. So there is some nonlinear integral equation for the function that you should solve, and then you can calculate it. So out of symmetry, this function is actually the function of two scalar. That was supersymmetry, but it depends on two scalar variables. And it has a very nice physical meaning. If you do some Laplace Fourier transform, it will become distribution of imaginary and real part of Green's functions. It's just let me finish the slide, and that's it. And this equation then becomes, so that's in this form supersymmetry we got us with Jan along with a studying problem on infinite Bethe lattice, but after this transformation, it's identical to the equation of Abhishek, Randers, and Saulis that derived it in a totally different way, but since it's correct, they're identical. So technically it's why, since n is here, so that's a technical answer. And physically, yeah, you don't expect that I will get from saddle point equation some properties of matrix with, I don't know, 4 sides. Yeah, that's so there should be. Oh, you ask why do I have, no, I don't understand. You ask why do I have saddle point at all, or why do I need large n for saddle point? Yeah. So once again, so first of all, I need large n because large n is here, and I think it's not surprising. Now, why do I have saddle point at all? Okay, so once again, that's a specialty of the model, yeah? So since I defined a graph with all with fully random, up to this connectivity, this helps me. I mean, this is, but physically it's also clear that I have some connection to the Bethe lattice model. It's not surprising because locally it looks like a Bethe lattice. So it's not what should be totally surprising, but it's nice there is a technical way to do it. Okay, so now I can just use it and calculate. So what do I get? In the localized phase, okay, there is just a single saddle point, and I get the inverse participation ratio, which is just a number of order unity. I can calculate, express it through properties of the saddle point, but it's not surprising. The inverse participation ratio is 1, of order 1 in the localized phase. Interesting story is in the delocalized phase. Then the theory has spontaneous symmetry breaking. So the localization, delocalization transition in this language is spontaneous symmetry breaking phenomenon. So I get a manifold of saddle points, not just one saddle point, and I have to integrate over the whole manifold. There is a symmetry group which is in this language some internal supersymmetry that I'm not sure that's it's a symmetry in this internal space that we introduce it. If it would be replicas, it would be some symmetry in replica space. But for me, it's so I don't have. I have time to explain it. So just believe it to me. And when you do this calculation, in the end, you get the inverse participation ratio that scales like 1 over n, which is this ergodicity that I claimed, and that's with a prefactor, and the prefactor is given by nu squared, so squared averaged local density of states in the infinite Bethe lattice problem. So I established a connection between this RRG model and the infinite Bethe lattice problem. So inverse participation ratio in the RRG model is 1 over n times this nu squared averaged on the infinite Bethe lattice. Now, this quantity can be calculated numerically by solving this equation. In general, I will show you how that we do it. But one can also study analytically how it behaves near the transition. So this is exactly this correlation volume that I showed you. It diverges exponential of square root near the transition. So the inverse participation ratio scales like 1 over n, but the prefactor diverges near the transition as it should be. That should be some matching with the localized phase. Okay, so now we have this exact relation, and we can also do it for other correlation functions and also test them numerically. So let me show this. Yeah, so this is a single wave function correlations. I just take one wave function and correlation at 2 different points. Now, in the localized phase, this goes exponentially with the system size, with the distance r, which is not surprisingly, but I will be particularly interested in the delocalized phase and critical point. In the delocalized phase, I also get, so this exponential factor is always here, and that's just, it should be there just because of some normalization. It's related to the connectivity. So there is m to the power minus r divided by r3/2. That's a property of how it behaves in the delocalized phase up to the correlation length psi. This is a length which diverges at the transition with exponent 1/2. So now I can just test it numerically, just an exact diagonalization, and you see exactly, so this what is, it's a logarithmic scaling, and that's exactly this scaling corresponding to this. Also, we can see this correction to this exponential factor, so it all agrees very nicely. And there are dots here, which I barely seen. They're exactly on top here and slightly shifted here. So these are results of the solution of the self-consistency equation, yeah? So we see that we have just a full, that's the way in which we get prove the ergodicity, but we can also check that the prefactor in front of 1 over n is also fully correct. So here, there is a small deviation, and that's because the system is already big enough so that exact diagonalizations start to make errors. Okay, so in the same way, I can study statistics of different wave functions at different points or same point. So for example, what is shown here is a statistics 2 wave function is a given point, but with different frequency. So that's kind of dynamical scaling. And this dynamical scaling at criticality is 1 over omega times some logarithm that we were not able to prove analytically, but numerically, we see that we know the exponent of this. And this logarithm is very important. As I will just show in a minute, it's related when I Fourier transform to time, there will be exactly what will determine the logarithmic scaling, slow logarithmic dynamics with time. And on the delocalized phase, this correlation function for omegas smaller than some correlation, this omega psi is inverse correlation volume, is just a constant. And for larger, I have critical scaling, yeah? So that's different for different disorders. I see this, I see critical scaling up to some omega, and then it saturates because I reach my correlation volume. So that's a crossover from critical regime to the ergodic regime. Again, there are dots here, which are resolution of the self-consistency equation, which are perfectly green. Actually, the last line, so these three lines are from numerical exact diagonalization, and the fourth line is self-consistency equation, but they all will agree because for this disorder, the exact diagonalization is 13. It's still a lot till critical point. Critical point is 18, but already we cannot do it fully controllably with exact diagonalization. Okay, and then I can generalize it to the whole R omega plane. So you have two correlations with different points, different frequencies. And basically, its result is just a combination of scaling with frequency, scaling with R.Bf. And so there is this phase diagram of regimes where you have strong correlations. And yeah, so there are two regimes. One is more or less critical, where the length related to frequency is smaller than the correlation length. And another is metallic, so to say, when the correlation length is smaller than the frequency related length. All what you expect from general consideration, what you expect from. It's all, on one hand, very similar to what we have in d-dimensional Anderson transition. On the other hand, it's very singular because some power laws become exponential or logarithms, and so it's not so easy to get all this just of, it's in certain sense limit d to infinity, but very singular limit d to infinity of the Anderson transition. Okay, so yeah, so this beta of omega that I call the omega-dependent correlation function can be used to calculate the return probability. Now it's, imagine I create something once in a given state, on a given point on my lattice, and ask what is the probability to be at this point in this state after time t. And again, we can study it using this analytical approach and then self-consistency equation, or just exact diagonalization. So the results are as follows. So let me show you first. So in the delocalized phase, the probability goes exponentially with the time. Basically, you diffuse on this lattice, but diffusion on such a lattice is kind of more or less ballistics. And since the number of your neighbors on the distance t grows exponentially, then the probability to stay at a given point is exponential. This time, not surprisingly. And that's exactly what you get here. Then, of course, at finite system, it saturates. After a time that I would call Thouless time, that's a time to reach your system, which goes logarithmically with the system size. Logarithmically with n, with a set of size of your Hilbert space. It's just a distance between the most distant points because you move essentially ballistic. At the critical, so it's a very fast decay at the delocalized phase. At the critical point, just the opposite. It's extremely slow decay. So first of all, at critical point, you go to a constant. Critical point is essentially localized. We just learned it from Ramanujan. It's exactly what you see. Critical point is very much similar to localized. You go to a constant, like on the localized side, and you approach it extremely slow. So there's a very slow logarithmic dynamics at the critical point. Yeah, you can do also spectral statistics in this way. So basically, yeah, so what is shown here is some normalized level number variance. For those who knows, it's more or less the same as spectral compressibility. So this is a quantity which is 1 for the Poisson. And in the Wigner-Dyson or random matrix theory, it goes down like 1 over omega. And that's a sketch of what we get at the delocalized phase close to the transition. It goes first, we can prove that at first random matrix theory, up to, the system is ergodic, so it's random matrix theory up to some scale, big scale, much larger than the level spacing. But then it goes up, so we can also calculate this regime, and then saturates here, and here it's close to 1. And this is a critical regime, and the critical regime, large frequency, it's critical. They expect like localize it, so this is 1. And basically, this is the numerics which shows this. However, it turns out extremely difficult to have all these three regimes in one exact diagonalization. Either you get this, or it's just our systems are not big enough. But we can check all parts of this behavior, and this is, for example, the critical part, which corresponds to this one. And at critical regime, we have again this logarithmically slow approach to unity, which is again manifestation of this logarithmically slow dynamics at criticality in these models. Okay, so now let me say a few words about critical behavior now. I told you that this exponent is 1/2. So how does one prove this? Yeah, so basically the proof goes like this. So the self-consistency, yeah, we want to know the critical behavior of psi as a function of the distance to the transition. So the self-consistency equation can be, to find this, we need to know some eigenvalues, the largest eigenvalue of certain integral operator that I will not write here, and one can show that this eigenvalue of the integral operator, one can expand it around this critical point. And then using this expansion, so let me just believe me, that's correct. This is some simple algebra. So in the end, what you get is that the logarithm of the correlation volume scales with the critical index 1/2, and we can also find all the coefficients. So basically, the log of the critical volume is a number that we know. Okay, that's a number for a particular lattice. It's given with a box distribution of disorder, the connectivity 3, and the middle of the band. Yeah, so then we just have number and 1 over square root of the distance. Yeah, so now we can test this. Yeah, that's analytical result. Let's see how close we come to this. Yeah, to see. To check this numerically, so first we should know where actually the critical point. So I told you already, to determine critical point of exact diagonalization is a nightmare. You will have a huge error. Yeah, that's so. However, we can get it by using again this integral equation by using the condition of stability of the localized phase. For this, we just need to calculate some eigenvalues of a linear integral operator, which can be done with a very good accuracy. So that's the result. So that's the accuracy with which we know the critical point here, the 0.1%. And that's one can do it better if one wants, but this is not needed. This is accuracy sufficient. Yeah, so if I would do exact diagonalization, I would probably get something like 18 plus minus 1. That's probably the best one. So now this is the behavior of the correlation volume as a function of the disorder. So 18 point something is a critical point. The correlation volume increases and diverges at the critical point, and see what is the value of the correlation volume that we reach here. It's a 10 to the power 19. So this is done by using the population dynamics for this integral equation, and of course, it's much, much more than the largest one we can reach with the exact diagonalization, which will be 10 to the 6 at most. And that's now, this is the analytical result, the asymptotics. And this is what we get out of this population dynamics numerics, and you see it nicely approaches this asymptotics. However, you need to reach really large, so this tau is log, not shown here, it's a log of distance to the disorder, to the critical point. So you really need to come here to this region to see this correct slope, and the slope is shown here. So in this part, the slope is totally wrong. It's twice wrong, but then it approaches this correct value, 1/2. Now, if I'm doing exact diagonalization, where I'm on this plot, I'm roughly here. That's the largest system sizes I can reach. I'm roughly here. So you will be wrong by 100%. Okay, so I have 5 more minutes. Oh, 1. Okay, so let me, yeah, so that's essentially last, well, 2 or 3 slides. So let me try, so maybe if you give me 2 minutes, quickly. So, because I think it's important, analogies between RRG and many-body localization, what are lessons? Yeah, so first of all, let me show you, that's a plot I already showed you, the level statistics, and that's a similar plot with MBL model by the group. Yeah, I think that's the group that did best numerics on this, and you see it's a very, very similar behavior. You have a crossing point that drifts if you look at this closely, and approaches, it goes down to Poisson. So they put the critical point here. And this is a crossing point at largest value of the system sizes. So this would correspond to this. So we know that it's larger, and I'm pretty sure here it's also larger. Now, how large is it? Strictly speaking, out of this, you don't know this. So I have some other evidence for totally different work by doing dynamics with time-dependent variation principle on matrix product states. And so this is a result. Let's an exponent that characterizes the decay. When it comes to here, 10 to minus 2 is essentially 0. It's our error. Then we are at the transition. For small systems like 20, it gives a transition like 4, which is more or less the same. However, when I'm going to do it 50 or 100, this data agrees and place a transition as roughly 5.56. Of course, it doesn't prove that this is a transition, but it shows the size of the finite size effect for sure. And so I think the best estimate for the transition that I would put would be something like 5.5 or 6. That's what we do in this paper. And once again, the critical point is, in both cases, essentially localized. So another similarity is the ergodicity of the delocalized phase. And that's, again, same group, but more recent work. And if you are not too close to the transition, if you don't try to approach, then you see that even, so this slope 1 here corresponds to slope 0 in my plot. It's different plots. So this is a relatively big disorder. Slope 1, it's ergodic. So larger disorder, it's first not 1, but then it becomes 1. And here again, it's first not at all 1, but then it becomes, and that's exactly the same sort of plots as we show here, but it's, so 1 here is 0 here on this plot. It's just different plot. Huh? However, of course, if you come closer to the transition, you will not be able to reach this ergodicity for your small system sizes. But it's not because system is not ergodic, it's just your system is too small. And that's, in this sense, they are extremely similar. Yeah, the critical behavior is, actually, I did not discuss this, actually asymmetric on RGs. There are different exponents on both sides. And these are numbers that this guys find. And other people find similar numbers in the order of 1 or more than 1. And we know that these numbers are just strongly violate Harris. Yeah, they cannot. And that's, again, another manifestation that we work with very, very small systems. Might be that just these small systems are just much more similar to RRG that one could think just, but that's just an absolutely wild conjecture. I don't insist at all. Yeah. Okay, now there is some connection, better connection with, yeah, I know I should stop. I will not discuss this, with a long-range interaction model where we can, using connection to RRG, put it on somewhat more a solid basis, although not fully solid, and then derive how the correlation, how the critical disorder scales with the system size. That's the situation when there is no transition in the thermodynamic limit, but there is a scaling of WC. You can derive how it scales with L. There is no transition at fixed disorder, but there is a scaling of critical disorder with the length, and we can use RRG, mapping to RRG to derive it, and it seems to be very much consistent with the numerics. Okay, so let me summarize. So we started localization transition on random regular graphs using exact diagonalization, analytics, and analysis combination with population dynamics with full agreement. The delocalized phase is all ergodic, but the ergodicity achieved for system sizes larger than nxi, which diverges in this exponential way at the transition. The critical regime is of nearly localized character for n smaller than nxi, so there is a very peculiar crossover from criticality to ergodicity. Yeah, so we have all details of eigenfunction, fluctuations, correlations, level statistics. Yeah, RRG is in a sense an intricate limit of Anderson localization in d dimensions. The critical index on the delocalized side of the correlation length is 1/2, and so we did it also numerically with population dynamics go into correlation volumes up to 10 to the power 19. And finally, last but not least, one can think about RG as kind of toy model of many body localization, very different toy models. Remember, also uses the word toy model. It's totally different toy model, but still. There are some more quantitative connection to long-range MBL and strong qualitative analogies with short-range MBL. And the important lesson is that we have very strong finite size effect, and exact diagonalization numerics can be extremely deceptive in a broad critical regime on the delocalized side of the. Sorry for being a few minutes longer. Thank you very much.
Thank you very much. Questions? Yes.
So how do you get rid of random graph geometry when you obtain your supersymmetric model? That's some sort of approximation, right?
No.
Or
it's not an approximation. So we average. So when you derive this, this action, you average over all realizations of random graphs. It's a result of averaging. That's exactly what helps actually. That's basically you say there is a graph which is totally random in a sense. Every link can be 0 or 1, and you impose a connection that sum of all links attached to given vertex is given number, like 3. Yeah? And once you do this, you can do this formal derivation exactly. Yeah? So this helps. Yeah. So we do it on a random graph, but then the statement is that random graph is what you want. Yeah. So when you average over everything, you essentially get a physics also on a typical graph, and the typical graph is what is locally a tree. But formally, we average over all graphs in this derivation, and also in numerics. Mm-hmm. 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 Yes. Yes. That's. You mean, basically, do I understand your question correctly? Imagine I would only have exact diagonalization data. Yeah. Would I be able to conclude that the critical point is here and not here? Yeah. No, I think probably no. Yeah, it depends how you extrapolate. Yeah, I think no, I would not. Well, of course, I know exact results. So, okay, maybe one can do the following. Maybe with knowing the exact result, one can try to find what would be how to proceed, and then test it to some other value of connectivity, and then check by yeah, maybe one should do this. Yeah, no, I don't know how to do this. I know this only from exact solution, but I don't know how to get it out of this. Yeah, I mean, you can roughly estimate if you do, of course, some, but it will very much depend and yeah, okay. Which plot? This one? Okay, yeah. So, good. So this is a decay of the imbalance. So now it's a totally different work. Yeah, that's I show you. So basically, you start from the state which is spin up, spin down, spin up, spin down, antiferromagnetic order, and you look how this imbalance decays with time, and you do it with PDVP. And so what you see, this decay is more or less given by some power law. Of course, we don't know whether it's really asymptotically power law or not, since we can do it only up to time like, I don't know, 200, 300, something like this. Yeah, but up to this time, it looks like more or less reasonably some power law, and you feed it by power law. And this beta is this power law. That's what other people also did. Yeah? And now this power law is loaded as a function of W. At the critical point, it should presumably vanish to go to 0, because on the localized phase, imbalance should be constant. So basically, we should ask a question where it becomes 0. Now you should say, what is 0? So there are two measures of 0. One is just our error. And second, yeah, there are these dots here, which correspond to non-interacting case. So we just did the same for non-interacting when it's just 0 identical. Yeah? So now we have a measure of roughly what is 0. So basically, everything which is below here, I would say is 0. And so when it's roughly, that's an estimate for the critical point. Of course, with the assumption that this dynamics that we see up to this time is real and not some intermediate regime. I should always for every numerics one should give this disclaimer. Of course, yeah, that's. This value fits very reasonably. So this is a small system like 20, and it's roughly the same value that people get here. So which I think is consistent, but then now we see how it still changes when you go to larger systems.
Cool. Thank you very much.
Yeah, thank you.